ensuring safety, achieving consistent product quality, and increasing productivity. These are the challenges facing industry today. From heavy industries such as automobiles and steel to precise processes such as chemicals and pharmaceuticals, modern industries share the goal of safety, quality, and productivity. Automatic control systems have played an important role in helping industry meet these goals. Although their products and processes may differ, all industries need a way to achieve reliable control of the variables in the production process. And technology has been the key to providing precise and reliable control. By utilizing technological advances, the instrumentation and control industry has kept pace with the needs and dreams of modern industry. How have automatic control systems changed over the past few decades? They've grown from feedback loops that controlled a single production variable to systems that provide integrated and coordinated control of an entire facility. In other ISA programs, we've seen how early control systems provided on-off control for individual variables. The development of the PID controller provided 3 control modes for more precise control. This allowed a transition from batch processing to continuous production. The PID controller became the standard for reliable and precise control of a basic feedback loop. However, more advanced control methods allowed the basic feedback loop to grow in complexity. Control techniques such as ratio, cascade, feed-forward, and adaptive control can provide rigid control for several variables in a process. By incorporating the latest technology, instrumentation and control systems have been able to provide the control required by modern industrial processes. Let's look at a small chemical company that's been growing rapidly over the last few years. They've utilized advances in technology to solve production problems and to keep a competitive position in their market. As a result, this company has grown from a small producer making one product to a large and profitable company making a diversity of products. Now the company is again in the midst of change. But today, instead of responding to problems, the company is enjoying the success that modern instrumentation and control technology has helped them achieve. Because of their success, they've exceeded the capacity of their current facility and are planning the design of a new plant. The company president has decided that the new plant should incorporate the latest in control technology. What will this mandate mean for our chemical company? Most certainly, it will mean utilizing digital technology as an integral part of their control system. In general, microprocessor-based equipment and digital control systems are replacing traditional pneumatic and analog electronic instrument systems in many plants. What are some of the changes that a control system utilizing digital technology might provide for a plant such as our chemical company? One of the major advantages of a digital control system is the coordination of control between the various process loops in a plant. There is a central point for operation and control at the operator's console. Consoles can be located in one centralized control center or in several centers throughout a facility. Either way, the operator's stations provide a way to coordinate control within a plant. A digital control system can be used to acquire data from the processes in the plant, store the data, and continuously update it. The data can be displayed on a CRT screen at the operator station. Using the CRT and the accompanying keypad, an operator can call up a display that shows the status of several control loops. The display format allows operators to determine at a glance conditions that affect the process, such as measurements, set points, and alarm conditions. Other display formats graphically depict process conditions so that the operator can see a loop when a disturbance occurs. In a digital system, control loops can run automatically, and the console condenses and displays control information in a relatively compact space. This versatility allows an operator to monitor a large number of control loops more effectively than with analog control systems. Changes to the process can also be made from the console, such as adjusting a set point or changing a signal to a control valve. These changes take place instantaneously, and the new data is available immediately throughout the system. The effect of any change can be observed at the console. Because the entire system has up-to-date and visually displayed information, control is more reliable and precise. Another advantage to a digital control system is the flexibility it provides when alterations have to be made to a system. Before we talk about how it's done in a digital system, let's first think about how system alterations would have been made in a conventional analog control system. To implement a different type of control in a particular loop, a new controller would have to be installed, connected, and properly adjusted. But in a digital control system, changes can be made with much less trouble. A digital control system can replace separate controllers as we've known them with something called control algorithms. A control algorithm is a computer program that provides a desired control mode. For example, a PID algorithm can replace what we've known as a PID controller. There are terms in the equation representing proportional, integral, and derivative control modes, the same modes we used in our conventional analog controller. So to install a new controller, it's only necessary to call up the appropriate algorithm, enter the necessary information about the process, and be sure that the necessary connections to field devices are in place. This process of setting up a new control loop with a digital control system is called configuring. Anyone authorized to access the system who is familiar with the process and its control needs can configure a new control loop from a menu, a series of questions presented on the display screen. Configuring can be done from the console, or in some systems, from a personal computer. Personal computers utilizing specialized industrial software are finding increasing applications in industry. Because of the flexibility afforded by digital control systems, potential changes can be tried out before a definite decision about a control technique is made. Engineers can more freely experiment with advanced control techniques since these changes can be done by configuring rather than by purchasing new equipment, installing it, and connecting it to the process. Another aspect of plant operations that would see changes with the installation of a computer control system would be the area of record keeping. A computerized control system usually provides a way to acquire and store data about all sorts of operating parameters, such as production rates, energy use, or product quality statistics. A digital control system can accumulate this data, then organize it into a log or report. For example, flow rates could be shown for a desired time period, such as hourly, daily, or month-to-date. Many digital control systems have additional computational power to manipulate this data. For example, to show means, standard deviations, or trends in process variables. In many cases, the computer system can be instructed to print reports at scheduled times and upon demand. These reports can be used by key personnel to provide an accurate picture of what happened during a particular time period and to help focus attention on critical areas. Once data about a process is collected and stored in the computer, it can be used in a variety of ways that make the operation of the entire control system and even the entire plant more efficient. In many cases, the computers that are part of the control system can be used to collect information from the process and use this information to generate schedules for production, maintenance, or inventory. Because of the improvements possible for our chemical company using digital technology, the managers of the plant decided to implement digital control in the new plant. But what type of system to install? Several of our engineers have been investigating different types of digital control systems. Let's see what they found out. Basically, digital control systems can be divided into direct digital control, often called DDC, supervisory control, also called set point control, and distributed control systems, often called DCS. Let's start by looking at direct digital control. This block diagram shows the basic components of a direct digital control system. In direct digital control, there is one central computer that has full control of the process. Connected to the computer are field sensors, here labeled with an S, that collect information about a measured variable. The computer is also connected to the final control elements in the system, here labeled FCE. Final control elements are often control valves. The computer receives information about the process from the sensors, determines what control action is necessary, if any, and sends this information directly to the final control elements. Other devices, such as analog to digital and digital to analog converters, enable the computer to communicate with individual control loops. Multiplexers, labeled M here, may also be used in the system to select and transmit data from the various field devices when specified by the computer. Multiplexers can reduce cabling necessary because they permit more signals to use a single line. In a direct digital control system, the central computer has full control of the process. Control parameters, such as set points or changes in the system configuration, can be accomplished from the console. Often, system tuning and troubleshooting can be done from the central computer. And the centralized computer used in direct digital control usually has the ability to perform complex logic functions and/or computations. Despite the advantages of direct digital control, its dependence on one central computer is a definite drawback. This means that any failure or malfunction in the central computer may result in a shutdown of the entire system while the problem is located and corrected. Because of this, a backup system may be required, which of course can add considerably to the cost of the system. So, direct digital control can be effective, as long as the central computer functions properly. What about supervisory control? Supervisory control is also structured around a central computer that communicates with many different control loops. But in supervisory control, each of the individual control loops has its own controller to monitor the loop and maintain the process as specified. As in direct digital control, the supervisory control system will include analog to digital and digital to analog converters to enable the computer to communicate with the individual control loops. Each control loop operates independently, but is subject to intermittent corrective action from the supervisory computer when necessary. This corrective action takes the form of set point changes. When the computer alters the set point, the controller then alters the manipulated variable to return the process to set point. In a supervisory control system, the system can continue to operate even if there is a malfunction in the central computer. Each controller continues to operate using the last set point value received from the supervisory computer. The process will be maintained under its current operating conditions, even while the supervisory computer is out of service. In this type of system, only the supervisory computer can change operating conditions or perform analytical or computational operations. The supervisory computer can communicate with the individual controllers, but the controllers generally cannot communicate with each other. In supervisory control, then, a central computer is used to direct the operation of individual controllers. Both direct digital control and supervisory control are structured around a central computer. Distributed control systems are not. Although the specific arrangement of components in a distributed control system can vary greatly depending on the process application, this drawing can be used to illustrate the basic principle. In a distributed control system, the control function is allocated to several microprocessor-based control units.